So what I want to just talk about a little bit today, this is a picture. This shows if you track a planet in the night sky, you can sometimes see that it appears to have some retrograde motion, which means it goes backwards. Like if you look at the stars just track across the sky in nice streaks, right? If you left a time-lapse camera open all night, you would just see a bunch of stars, you'd see streaks across the sky. And most of the time that's what you'd see for planets too, but every once in a while you'll see something like this, where the planet will be tracking across the sky and then it's going to appear to jog backwards a little bit and then go forwards again. And so this was a big deal. This was first noticed by, anybody know?
LA.
No, that's close. Contemporary. No, that's not such a good guess. Nicholas Copernicus was the first person that saw this. He witnessed this retrograde motion, and he got to looking at this and exploring it, and he and some other astronomers realized that the only way that really could happen is if Jupiter weren't rotating or revolving around the Earth, if it were revolving around the Sun, and we were mutually revolving around the Sun. That's the only way you could really explain that kind of motion. And so that was a big deal. I mean, that caused huge uproar. The people that said stuff like that in that day and age were typically locked up or strung up, or I mean, it was because that went contrary to what the Catholic Church was telling everybody that was the way things were. So that was a major revolution. But it really kind of changed everything. When they started to notice this and people started to look for some other ways of describing the motion of the planets as being heliocentric around the sun instead of being Earth-centric, right, around the Earth. Then all of a sudden things started to make sense. And smart guy, good mathematician named Kepler, he came up with the laws that describe the way that planets orbit around a star, for example. Or it doesn't be planets around a star, though. It could be anything orbits around something else. And here's a little summary of what the laws say. Let's just write out of your textbook. So there's 3 laws. First one just says the paths of the planets are ellipses with the sun at one focus. Okay, now let's just pause there for a second. I just threw together a little geometer sketchpad document so we can kind of mess with this a little bit. If I open this up, here it is. And so here we've got let's just say that's a planet in orbit around a star. That's a pretty circular orbit, right? Okay, but the thing is, circles are ellipses, right? They're just special ellipses where the 2 foci coincide. If I pull the 2 foci apart, foci is just plural for focus, there's one focus and there's the other focus of that ellipse. Okay, and then what you notice now is that the orbit is elliptical. Okay, does anybody know what the definition of an ellipse is? Like how we could come up with a very, very simple rule. You could make an ellipse anytime you want to with 2 nails and a piece of string and a pencil. What is it? A freehand circle? Not exactly. How can you do that? Do you know what an ellipse really represents?
You put the 2 nails in right there, and then you take the string.
Karen Deminu, please call extension 3804.
Yeah, that's it. All you have to do to make an ellipse is I could put a nail in there and a nail in there, and I'm gonna create a loop of string, stretch it tight, and there's my pencil. And then as I draw this thing around the outside, and I keep it tight the whole time, it's going to create an ellipse. Now, what did we just do? Why does that work? Well, it works because an ellipse is defined as, let me get my board back here. An ellipse is defined as the locus of points. So it's going to be the set of, it's just a fancy math word for set. It's a set of all the points such that the combined distances from one point and another point are always the same. Okay, so if I call this one, let's call this D1, and that D2, the sum of D1 and D2 is always going to be the same. So if I go over here a little bit, oops, I'm not going to do that. There you go. If I go over there a little bit, now they've changed. Now that's D1. It's gotten smaller, but D2 has gotten bigger. And so the sum is always going to be the same. So that's technically really what an ellipse is, if you want to think about it in its simplest form. It's just a set of all those points that fulfill that one criteria. Yep.
What's the, formula for D1 plus D2, what is always equal, or D3?
Well, the formula for an ellipse is just this. Formula for an ellipse is just like, it's x minus h squared over a squared plus y minus k squared over b squared equals some constant squared. Call it r squared. I think that's right. It verbs have done this. And that's just, these are just the distances of the major and semi-major, or major and minor axes. It's a semi-major and semi-minor. So the distance from the center of the ellipse to here to, that's be the semi-major axis, from there to there would be the semi-minor axis. You might have written that wrong, actually. I can't remember exactly.
Where would they go?
Say it again. So they'd be, well, this would just be, that's a good question. So this is just the solution set to all the values of x and y that would satisfy that equation. If we just graphed them all, they'd form that closed ellipse. So all the infinite points, like if I chose a certain x value and said, okay, what's going to be the corresponding y value? Well, if that's my x value, then my y value would have to be either there or there. Okay? So it's, anyway, that's way more math than we're going to do. We don't need to worry about all that stuff. Really, all we're concerned about, is just, that objects orbit each other, like an object orbits, and really they orbit each other, right? Technically, both of these objects orbit each other. This one in here would wobble around a little bit. If it's really massive, it wobbles very little. Like if we look at a star and a planet, the star is, millions of times more massive than the planet. And so the star doesn't appear to really move. It does wobble a little bit, but it doesn't move very much. The planet moves a great deal because its mass is so light. If they had equal masses, then they would revolve around each other like that, right? But an object orbits another object in an ellipse. And so this would be, this is not what our Earth's orbit, is it elliptical or perfectly circular?
Elliptical.
It's slightly elliptical, yeah, just not very much. We are a little bit further, we're a little bit further away from the sun, I believe, during our summer, I think, in the northern hemisphere, I believe. Could be wrong. That's not what causes the seasons, though, right? Everybody knows, right? What causes the seasons? Yeah, okay, that's the axis, isn't it, right? So the fact that it's really not how far we are from the sun, because it's not a very big difference, but if the Earth is tilted so that the northern hemisphere is tilted away from the sun during part of the year, well, that's going to be the part of the year where we don't get very much sunlight, direct sunlight, and so it gets cold, right? It really has nothing to do with the elliptical orbit. But all the planets are pretty circular. I mean, they're not very elliptical. Then we know the term. You guys probably haven't talked about this a lot. Maybe in pre-calc, we would talk about this a little bit. The term for how distorted an ellipse is. How stretched, yeah, because this is not a very, to use really technical words, that's not a very ellipsy looking ellipse, is it? Right? That's more circular, right? You make it look much more elliptical if I
think you went over the formula for an ellipse in pre-calc.
maybe did spend a lot of time. It's called the eccentricity. Eccentricity tells you how distorted is it, how obvious an ellipse is, right? What's that? What's that? Okay.
No
you
question.
really oughta
The
hear it.
only stupid question is the one that's not asked.
Oh.
This is a learning environment.
Well, if she can ask the question later, if she feels braver. That's fine.
Yeah.
Anyway, so the eccentricity tells us how far apart, essentially, in relation to, the size of the ellipse, the foci are, right? So can anybody think of a certain kind of, that's really not much of a, planets don't really have typically highly elliptical orbits. But comet would, wouldn't it? Comet is a good example of something that we see quite often. We see them in the sky routinely. Comets have highly elliptical orbits, right? What do you know about comets?
They
Really show up like every few months.
They don't show up very often. Like Halley's Comet only shows up once every 80 years or something, right? I don't know exactly what it is, but it's a long time between when it makes an appearance. Where does it go when we can't see it?
Away.
Long ways away. They reside out in what's called the Oort cloud, which is way far out beyond the extent of our planetary orbits. How come they take so long to get back? What's going on?
They're in that system way really far apart.
They're moving so fast. Okay, but if they were, because they come zipping by the sun pretty fast. I mean, they don't last very long. Halley's Comet only lasts for, a couple weeks or something, and then we've seen it go all the way from being sort of midway out through the planets back again, and it's going pretty darn fast. Really fast.
Speeds up and
Oh, okay, do that again. What's it doing?
it's like speeding up, you wanna go around the sun and then have slingshots back.
And then it slingshots back out. And what happens to its speed as it gets further away? Slows down. Okay, we can kind of think about this now. If we want to think about the orbit of a comet, think about the forces acting on the comet. So let's say, okay, let me get it out. I gotta wait. As soon as is everybody ready to learn about comets?
Yes.
All
You
right.
should watch The Martian. She doesn't watch.
Watch the Martian. So there's our sun, right? There's our beautiful sun. Here's some comet coming flying in, and the tail's always pushed. It's always kind of pushed backwards because the solar wind is ripping off particles from the comet. Its tail's off away from the sun. As it's coming in, what's the only force acting on the comet? Gravity. Yeah. So there's going to be gravity's pulling on the comet. As it gets closer, what's happening to this? Do you suppose? We haven't really talked about this, but what's happening to the strength of the gravitational attraction as it gets closer? Getting stronger. So as it gets in here, it's really pulling much, much harder on this thing, right? On this comet. And now it's really got a big tail. It's going really fast. And it's closer to the sun. So there's going to be a component of this force that's going to be along the direction it's traveling, and so it's being accelerated by the sun, isn't it? That makes sense, right? I mean, if we were to break this into components, we don't have to do all this stuff, but if we were, we'd have some tangent component that's pulling it forward, and then there's some other little component that's kind of causing it to turn around the sun, essentially, right? Causing it to curve, yeah.
Are we gonna look at centrifugal acceleration on an elliptical type?
No, we're not going to. But you can, I mean, we don't need to get that mathematical, but you get the idea that it's sort of the same thing going on, right? There's going to be, this is the part of the acceleration that's going to cause it, if that weren't there, it would just keep going, right? That's going to cause it to turn. What happens when it's on its way back out?
It slows down.
It's going to be slowing down because now the comet is actually traveling in that direction, right? But the force that's acting on it is opposite the direction. At least there's a component that's opposite the direction of travel. So it's getting slowed down by the sun's gravitational force, right? So just even using just that kind of logic, you could sort of infer that where is it going to be going its slowest? Yeah, way out there, right? Okay, that's where it's going to be going the slowest. Where's it going to be going the fastest? Right in there, yeah. Okay, and that's true. And that is essentially, that's qualitatively what Newton's second law is.
What's the acceleration of gravity for the sun?
The acceleration of gravity for the sun, there is no such thing. It depends on how far you are away from the sun.
I guess on the surface, like just to compare it to Earth's.
On the surface of the sun?
Yeah, like if you're walking
Oh,
around the sun at night.
It'd be, yeah, if you're walking on the sun at night, it'd be warm.
no.
But
Oh,
you-
no, Dave. Oh,
Where's he going?
oh, oh, Dave. Oh.
Where's he going?
Just, you do what? Oh, you gotta tell him that one.
Payne just
No,
looked over
take
at Lincoln and
notice.
was like, oh, I get it
No,
now,
stop.
because
Don't
the
say
sun's
it.
a star.
Oh,
So that's why he just walked out.
well, why should have walked out for that? It's a good revelation. The sun is a star.
So, a question real quick,
Yeah.
in like every space movie, they do like the slingshot technique around the planet.
That works.
How does that work though? Cause like if it's coming out and slowing down, it comes out like, where do they?
But they
Okay.
have external thrusters to offset the
The
external
external thrust like
thrust.
halfway through.
You settled that?
Yep.
Okay, no, what's really going on with that, the way you could use the slingshot effect is when you go around the planet's going forward. And so when you go around the planet, it's gonna impart a little bit of its forward momentum to you when it's pulling you back through.
Else you would make one whole thing around.
Right,
Okay.
right. And so that gives you, and it wouldn't even have to be a whole thing, but as long as you end up being shot out in the same direction the planet's moving, it actually transfers a little bit of its momentum to you, and it ends up going a little bit slower. But the spaceship goes a lot faster. Right. Okay. All right, so Kepler's first law, paths of the planets are ellipses with the sun at one focus. This doesn't have to be planets and the sun. It could be moons and a planet. It could be artificial satellites around the Earth, right? Number 2, this is the one I want to show you. An imaginary line from the sun to a planet sweeps out equal areas and equal time intervals. So I put links to all these on, why don't you guys put your phones away, please? I put links to all this stuff on the site. Oops. But look at this. This is kind of cool. Yeah, check this out. This is good stuff.
That is essential.
Okay, so look what this is doing here now. How does this work? So we've got the sun and we've got this planet. Right now, let's put the eccentricity at 0, which means it's a perfect circle. So what you notice is there for equal intervals, for 10-second intervals, look at the area being swept out. Well, it's the same each time. Is the speed changing though?
No.
It's not really changing, is it? But if I make the ellipse more eccentric, I can just use this little slider down here and make the ellipse much more eccentric. And now look what happens.
Whoa.
Okay, those are equal areas, but for those to
I think we would die.
for those to be equal areas, it's got to, when it's further away, it's sweeping out a longer area so it doesn't take as much speed, right? Like that green one right there is the same area as the red one.
Would you go so
Let me try something. Maybe it's easier to see if it's more like this. So those are going pretty fast seconds, but you get the idea.
Like, yeah, that'd be pretty sweet.
That's an interesting observation, though, that he made, and mathematically it works. That in equal time intervals, it sweeps out equal areas. So the closer you are, the bigger the angle you have to go through to get that same area, right? And that's kind of a visual way of demonstrating, that it's going much, much faster when it's close to the sun and slower when it's further away. Okay?
So, would our gravity change like a lot when we went around that fast part? Not at all.
What do you mean your gravity?
Like Earth's gravity.
No, you wouldn't.
So
I mean,
on
it's-
the daylight side, would it be like less? Or
Like
something?
at 500 degrees though.
Now keep in mind this is massively sped up, so you wouldn't really notice. You wouldn't really notice
On that
anything.
side right there that's close to the sun, on the side of the planet facing the sun, would the gravity be less than the side that's facing
Like
away
pulling
from the
y'all
sun?
up.
There would
Well,
be
you'd be spinning the whole time.
Because you'd have the gravity of the planet.
there would be some tidal forces from the sun would be much bigger than they are now. So you get pulled stronger on one side than on the other side of the planet. So it would tend to warp the planet a little bit.
Is that what? Zero gravity on one side.
Is that what happened with
It wouldn't go that fast.
the tidal waves? Just kind of crazy.
Uh-huh.
If we were to get that close to the sun, would the Earth
It got
rotate
too close to the
out
sun
and
and tidal waves just
and
went
then rotate?
No, its rotation would stay pretty much the same. Yeah. Okay, here's another one. This is kind of fun. Well, on this one, you can do, let's see, reset. Okay, so now there's the sun. And then this is on the site. This is kind of a cool one. You can hold down. I can hold down and I can start the planet with,
So it's like a better version of the one that we found, right?
Yeah.
which one did you find?
We found that one where you just click on it and then.
Oh,
you
yeah,
press
it
on
is. It is a better version of that, right? So you can start off like in which direction do you want this thing to go? Like maybe I just want it to go kind of like that. And that probably wasn't a good choice.
I agree.
Okay.
Okay.
This is kind of a fun one though. You can play with this one.
Another death.
This one's gonna be fine, I think.
Oh,
Oh, that's kind of spicy though.
You're hot.
Anyway, you can mess around with that.
That does not seem elliptical.
That's pretty elliptical.
This way,
Okay.
maybe.
And then what happens if I just let it go?
it doesn't move.
Yeah, it won't move.
It'll get
Oh,
sucked
no.
in.
We're dead.
There you go. Okay. And then this one wasn't so great. This one's on there too, though. There was one I thought that was really pretty cool, though. This is pretty sophisticated. I'll show you this other one. You can mess around with these. Where'd this one go? I'm not even sure.
Wait, so that one that me and Scott found, that one didn't produce ellipses, or at least not good ones, so it was really hard to get those.
Yeah, I think this is a little better.
It was really hard to produce an ellipse.
Like, was that just due to how they made the game?
Yeah.
I think that might just be because it was a game and not like this simulator.
I have a question about
Yeah.
stars and stuff.
Yes, about stars and stuff. All right.
The sun is star.
Like the conversation we
Oh,
had
here it
Friday.
is. Yeah.
Okay, so you know how you were saying that it takes like so long for light to get to Earth?
Mhm.
So if you took the light that we're seeing like off of these like so-called Earths that are just like ours, like millions and billions light years away from
Mhm.
us, how do we know if they're still there? If like, couldn't we just be getting like the
Okay, that's actually a really, really good question. So do you ever understand the question? So if you're looking at light that's coming in from very far away, the question is, how do you know that they're still there? Right. And there's two ways you could answer that. You could say you can't, but then in a probably a better way, more realistic way. The universe, if you can see them, then they're there because there's no way you could have known anything different. Information can only travel at the speed of light. And so really, a lot of times people say when you're looking at starlight from stars that are very far away, you're looking back in time. But that's honestly not the way I would look at it. I look at it a little differently. I would say, no, not really. What you're doing is you're looking at a younger part of the universe, right? Because the light just hasn't gotten to you. How do you know that it's still there? Well, because I can still see it. There's no way I could have ever gotten there to know any differently. And so as far as I'm concerned, it's still there.
So like, if we looked at a star and like the Big Dipper, the star is like obviously there, but if it exploded, like a supernova happened,
Mhm.
and like, would we see that happen in real time?
No, you wouldn't. If you mean real time, is like the time of an observer, somebody that lived around that star, right? No, you wouldn't. And so you really could never, from your perspective, the supernova only happens when you can see it, right? Now that'd be different than if you were on a planet around that star and it went supernova and you were killed.
Oh no, I'm talking about
Right, but the thing is, that's a different part of the universe, and they are gonna see things differently than we do, which is right and which is wrong. Well, none of them are right and none of them are wrong. It's one thing you have to really get a handle around in physics when you start to talk about quantum mechanics and general relativity and special relativity, is that the relativity is the thing that always shows up. The perspective is only based on your perception of reality is only based on where you are in the universe. And it would be completely different if you were somewhere else. And there's no preferred place, but the stories are never going to agree, right? And so it's a good question, and I would just say, in one manner of speaking, yeah, you can't really tell, but there's no such thing as simultaneous events, truly simultaneous events. And so in a more real way, you're not looking back in time, you're just looking at the younger part of the universe.
So
If you look far enough out there in the universe, right, the brightest objects in the whole sky are called quasars, and they're just proto-galaxies that are forming when there's lots of infalling material around the central black hole, and they're just super bright. All this stuff is falling into the black hole, and as it's being accreted, it's releasing a tremendous amount of radiation. But you're looking back, billions and billions of years, essentially. That's how long it's taken the light to get here. There aren't any more of those around in our part of they've all turned into galaxies, right? They're extinct in our part of the universe. But if you look way out there, you can look, it's so far back in time that you can see them happening. Was it really back in time, or are you just looking at the younger part of the universe?
Wow.
Right, see what I'm saying? Yeah.
So, they could be gone, like, just like, say there's none of them here, they're all gone here, they could be gone there, but there's like this space in the middle of the universe that they're still there.
Mm-hmm.
It's like,
Yeah,
wow.
yeah, from their right. I mean, from their perspective, here's just a simple analogy too. If you were to go out to, like, when we look at planets that are, let's say, eventually we look at planets, we develop these abilities to do interferometry, and we can look at these planets that are millions of light years away. Well, what if they were doing the same thing to us? What would they see?
They'd see
Not us. They'd be looking back at, cavemen. They wouldn't be seeing us, right? I mean, they're going to be looking into our distant past. So we're dislocated from them permanently in time. We can't ever shake their hands, right?
Because even if we did get there, it'd be too late.
Right.
So,
Mhm.
ignoring the reasons why you can't go faster than light, under the theory that you could you be able to effectively travel back in time consistently?
If you could go faster than the speed of light, theoretically you could, but you can't go faster than the speed of light. So it's a moot point.
Yeah.
Nice.
So that's what the Flash did, right?
The physics of the Flash is way beyond me. I don't know.
Okay.
I don't know. Okay. This is kind of a cool one. You have to mess with this one too. I think this one I just embedded in a page on Moodle. But this is kind of a cool one. You can do some pretty complicated things with this. So you can do. Here, look at the relative masses. The yellow mass is 200 units, and the purple one is 10. So it's only a 1 to 20 ratio. So you can really see the wobble of the star there, right? But you can do some other crazy stuff with this. You can do things like, how about doing a sun, a planet, and a moon?
Whoa.
So there's a moon going around a planet, which is going around a star.
So is
That's
that what
kinda
our
cool.
moon does?
Yeah. That is what it does.
So beautiful.
Is there part of the simulation that shows the entire solar system moving through space?
This one doesn't, it has quite a bit. You could do let's do a sun, a planet, and a comet. This is kind of cool.
Oh, is the comment the
Yeah, the comet is a weird one,
The
right?
one in the middle is the sun.
Will they eventually hit each other?
I don't know. You almost have to keep watching, don't you? Oh, we're saved by the sun. How about that? Good deal. Binary star and planets. This is kind of cool. So you got these two big stars and then this planet that's circling.
Well, you say that.
Anyway, that's. I thought that was kind of cool. That one's on there too. All right,
So
so
would it always be daytime?
well,
No.
planets that are really close to stars, yeah, then they get tidally locked.
Are there-
It is always daytime.
Are there solar systems?
Our sun is tidally locked around us.
Would it be
We only
possible-
see the same side.
Would it be possible to have a solar system with two suns?
Sure, that's a binary. That's what that was.
This is.
Wait, two suns or two moons?
Yeah, in fact, I think that pretty sure that one of the nearest stars to us is a binary. I think it's like Proxima Centauri and Alpha Centauri. I don't know. I mean, one of those is a binary system.
So logically, they'd probably have a lot of sand, I would imagine, right?
Everything goes back to Star Wars.
It does.
Okay, so here's the last
Oh my
one.
God.
All right, so the first two Kepler's laws are totally non-mathematical, right? You're not going to have any real work to do in terms of problems on those. But the third one is the one where we can actually use it a little bit. This is the one where the homework you do is based on this one. So this tells us that the square of the ratio of the periods, right, of any two satellites revolving about a common center. In here they talk about planets about the sun, but it doesn't have to be that. It could be about the Earth. Satellites revolving about the Earth, for example. Is equal to the cube of the ratio of their average distances. Okay, this ends up being useful, and there's really easy ways to deal with problems here, rather than having to do lots of number crunching. I'll show you an example. Like, what if we want to do a problem like this? Let's say that an asteroid revolves around the sun with a mean orbital radius twice that of Earth's. Okay, so it's revolving around the sun. It's twice as far from the sun as the Earth is, right? We want to make a prediction about the period of that asteroid in a year. So how long is a year going to be on that asteroid? If you're living on that asteroid, how long is a year? Right. What can we do? Well, the velocity is going to be different, but the velocity is what it is, right? There's a certain velocity that's associated with each of those orbits. The closer you are to the sun, the faster your orbital speed, right? The faster you have to move. And that makes sense. We can all,
the year,
right? We've all seen that before when you put those little balls in the little cone things. They get closer to the middle, they go a lot faster, right? Okay. So how are we going to do this? Well, let's just say, what's the thing that we're trying to find? We're trying to predict the period of the asteroid. So whichever one you're trying to predict, let's always put that on top of the ratio. Because what do the A and B stand for? Well, it doesn't matter. I mean, objects A and B. Let either one be A and either one be B. But in this case, we'll let A be the one that we're trying to find, which is the asteroid. That works out well, A for asteroid. So the asteroid is A, and the Earth is going to be B. Right? We already know all that information for the Earth, though, right? We know that let's measure it in years. What's the period of the Earth in?
60 days.
In years?
Or
How many years it take for the Earth to go around?
One.
Yeah, 1. So we'll measure it in years.
1.0009.
Okay. So then we could set this up where we could say the period of the asteroid divided by the period of the Earth. Whoops, not B. That quantity squared must equal the radius of the Earth. Oh, sorry, asteroid. Oops, got it backwards. Radius of the asteroid divided by the radius of the Earth cubed. Well, in terms of the radius of the Earth, what is the radius of the asteroid? They tell us up here.
Twice the
2 to
Earth.
1.
Twice, right? So R sub A just equals 2 times R sub E, right?
Yeah.
Everybody see that? So look what we can do then. We could, instead of writing this as R sub A over R sub E, let's just make this substitution. And then look what this becomes, right? It just becomes a number. So T sub A over T sub E squared equals 2 R sub E, right? 2 times the Earth's radius divided by the Earth's radius cubed. Well, how can I simplify that fraction?
2 cubed.
It's just 2, isn't it? Right? The radius of the Earth cancels, right? And so it's just 2 cubed, which is what? 8.
Oh.
Right? See how that works? And then now all we have to do, if we want to solve for this one, well, what is the period of the Earth? 1. We're measuring it in years. Well, let's go ahead and measure it in years. So this becomes 1. And so then we just get the period of the asteroid divided by 1 squared equals 8. So what do I do to solve for the period of the asteroid? Square root it, right? So we end up with T sub A equals the square root of 8, which is about 2, it's a decimal, about 2.8-ish. Right, I think, something like that. Right, so it takes about 2.8 years, okay, for that asteroid to make one revolution around the Earth.
Our years?
Of our years, yeah, 2.8 Earth years for one of its years. Okay? How could we do, try another one. How about this one? So here we know Mars is on average 1.52 times as far from the sun as the Earth. Predict the time required for Mars to circle the sun in Earth days. Well, let's just predict it in years first. We could always do a conversion. How much time we got?
1 minute.
1 minute.
Maybe let's not do that one right now.
Do it.
Anyway, I've got the stuff up for. I'll put the textbook up, the online textbook as well. Put everything up for chapter 8. First assignment's up. You can start on it tomorrow. You got a work day. Get back to this stuff on Wednesday.
Promise?
Promise. Pinky swear.